Alright, this video is meant to just go over the 5 trig identities that I mentioned during class. So the first one was cosecant theta minus cotangent theta is sine theta over 1 plus cosine theta. Alright, and we are going to, I think, work on the left side because technically this represents 2 fractions. So we have 1 over sine minus cosine over sine. And we got really lucky here that the denominator was already the same. So we could put these together into one fraction, 1 minus cosine over sine. Now if you look back in your notes yesterday, I think it was, I believe we did a problem very much like this. And it's very tempting to cross multiply. However, we are not allowed to, because to cross multiply would be to assume that the equals is a legitimate equals. And actually on this problem, we're trying to verify that this equals is even supposed to be here. So you shouldn't really be cross multiplying. But you can kind of do the next best thing. You can multiply top and bottom by the trig conjugate 1 plus cosine. So let's try that. You know what? If it doesn't work, then oh well, try something else, right? Okay, the top is a FOIL. The bottom is more of a distribute kind of thing. But I'm not going to do both. I never do both. I just pick one. And of course, it's the conjugate pair. So when you multiply the tops together, you get 1 minus cosine squared. And this is all over 1 plus cos times sine. Okay. And since I'm not allowed to touch the right side, I'm just going to write, little quotations there. Okay, the numerator, if you look at your identity sheet, you'll notice that the numerator here, 1 minus cos squared, does look familiar. It is just sine squared. So you can put that on here. Okay, now you can see why I did not distribute the denominator, actually, because now it's time to cancel something and the bottom is still factored. So if I had distributed the sign on the bottom, I think I'd be regretting it right now and pulling it back out again anyway. So now I have the final step. I get to write my favorite part, sine theta over 1 plus cos theta equals sine theta over 1 plus cos theta. And then you can put QED, which means, in Latin, it means quo etra, I believe, demonstratum, or which we had to show. And we did show. So this is what we had to show, and we did show it. Let's go to number 2. Okay, this one looks really hard because of the secants and tangents. And the scary thing is the left side and the right side are about equal complexity. So which side you're supposed to start on? The left side looks a little more complicated, I guess, since our left side has secants and also tangents, but the right side only has secants. So that seems nice. One thing you might want to do is just look at the more complicated side here, probably the left, and just decide what you're wanting to get rid of, right? You'll notice that the left side has tangents that the right side really doesn't have. So why not just go look on our cheat sheet and look for something that says tan squared, and maybe we can rewrite the tan squared here as something else, right? Okay, so I definitely want to get rid of the tan squared. Also, I would like only secant squareds in the answer, actually. So, boy, I wish I could find something that was like tan squared equals yada yada secant squared, you know what I mean? If I could find something like that, I think I'm home free. I'll just plug that in and it'll be all secants from there. Well, it turns out if you look at your identity sheet, there is such a rule. And it says tan squared plus 1 equals sec squared. And that looks a little different, but if you think about it, you can move the 1 over to the other side, right? You can always move the 1 over to the other side. Okay, so I'm going to replace the highlighted section with sec squared minus 1. And of course, I'm going to put it in parentheses. So now it looks like this. 9 sec squared theta minus 5 times sec squared theta minus 1. Not allowed to touch the right side. If I distribute the negative 5, you can see this actually worked out really easily, right? So some of you are having a really hard time with this problem, and I think I know why. I'm not a mind reader, but I think I know why. I think you tried to change perhaps both the secant squared and the tan squared at the same time. Now, if you do that, you're going to find yourself kind of getting all into a weird cycle of no progress, like a little rabbit trail, dead end, if you like. And there's no reason actually to replace the sec squared here. We actually like this sec squared here. We're expecting sec squareds in our answer. So I think you should have just left the 9 sec squared alone the whole time. See? All right, next problem. All right, this one is cosec theta minus 1 over cot equals cotan over cosec theta plus 1. So actually, if you kind of look at this one and compare it to 2 problems back, right here in our work, we had something very similar. We had a 1 minus cos over sine equals a sine over 1 plus cos. That looks quite similar to this scenario, just by, kind of resembles it. And if you recall, our trick a couple of slides back was to use a trig conjugate, 1 plus cosine. All right, so on this problem, why not use a trig conjugate? Let's use cosec theta plus 1. We'll times that to the top and to the bottom. Since we're not allowed to touch both sides, we'll just kind of do top and bottom instead. Like that. And we learned our lesson last time. We're only distributing the conjugate pair, which is our top there, numerator. You get cosec squared theta minus 1. The bottom, just leave it alone. Don't distribute it. I'll bet you anything that cot theta is going to cancel out here in a minute. If you look on your identity sheet, you will see cosec squared theta minus 1. It's on there. And it is actually cot squared. Cot squared. Okay, so that top is just cot squared. There you go. And very similar to a couple of problems ago, 1 factor of cot cancels out. And there you have it. Okay. Now, some of you paused the video and you peeked at your identity sheet, and you're probably mad at me right now. You're thinking, wait a minute, there's no cosec squared theta minus 1 equals cot squared theta rule. Well, you're right. Actually, this doesn't show itself on the identity sheet explicitly, but if you move the 1 to the other side like this, then actually this was on our identity sheet, wasn't it? So I'm giving you permission to use any of the top 8 rules on the identity sheet, the ones we've proven, and to shuffle them around. All right, next problem. I love the look of this problem. We have cosine theta over 1 plus sine, and we're adding to it its own reciprocal. It's just so cool looking. And this is somehow equal to 2 secant. Interesting. Interesting. All right. Let's see here. Ooh, well, if you think about 2 secant, right, you're not really supposed to touch both sides. I'm definitely going to be working on the left, but I can't resist at least thinking about this as 2 over cosine, right? And so mentally, I can think of the right side as 2 over cosine. And 2 over cosine appears to me to be just a single simple fraction. Now, the left side, though, is 2 very complicated fractions. So how am I going to turn 2 fractions into 1 fraction? I'm going to use a common denominator. It's kind of like saying, I've got 2/3. Maybe the teacher tells you, prove to me, that 2/3 plus 4/7 is, 26 over 21. Okay, well, to prove it, to show it, you would want to do a common denominator times this by 7, times this by 3, and then, make it work. Okay, so it's very similar to that. It's probably easier to take the left side and combine the two fractions into one than it is to take the right side in some magical way, dream up a way to split it up into two parts. Okay, so let's focus all of our attention on the left side throughout the problem. But start with the concept of least common denominator. I'm going to multiply the top and bottom of the first fraction by cosine, because that's the denominator of the second fraction. And for the second fraction, I'm going to multiply top and bottom by 1 plus sine. Let's just see what happens. So this is going to get times by cosine, which means I should probably put parentheses on the 1 plus sine. And this is going to be multiplied top and bottom by 1 plus sine, which means I should probably put parentheses on my 1 plus sign here as well. Okay, kind of messy, but the numerator is cosine squared theta, and the bottom is like this. And then plus, okay, then this next one's a full-on FOIL. Like you're going to have to do, first, outer, inner, last. You get 1 plus sine plus sine plus sine squared. And the only payoff that I can see here is now we can put these two fractions together, but this is starting to look pretty awful. Actually, let's cluster these first, and we'll put 2 sine theta, right? If you add a sine to a sine, you get 2 sines. All right. Let's join the tops together because we have a common denominator. So we have cosine squared plus 1 plus 2 sine plus sine squared. And then there's this denominator, cosine times 1 plus sine. Now you might say, why don't you distribute that denominator, Mr. Shore? Because I have a funny feeling that this 1 plus sign is going to cancel eventually. How do I know? Because I still remember what the right side was. It was a 2 over cosine, and by golly, this had better go away someday. Right? That 1 plus sign has to go away eventually. All right, so I'm not wanting to get too ahead of myself here, but I'm not expecting this 1 plus sign to last much longer. Let's look at that top. My goodness. 4 parts. That's terrible. Wait a minute. I see a cosine squared plus sine squared. Ooh, that's 1. Is it not? That's uno. Okay, so I have 1 plus 1 plus 2 sine theta. And the one that I just wrote right here comes from the cosine squared plus sine squared that I highlighted in light blue up above. All right, and now we can see that this is 2 plus 2 sine theta. And we can see that if we factor out a 2 to the front, the top is really just 1 plus sine theta. And then this cancels out with this to produce a 1 on top. Okay, so this is just 2 times 1 over cosine, also known as 2 times secant. And this is, I've kind of been lazy here, the right side. Actually, it's not so lazy. I'm not allowed to touch it anyway, so why even write it? You know what I mean? But notice all my work is done on the left. Like, I never actually modify what's on the right at all, and I work straight down the page. Okay, so I'm asking you, please work straight down the page. Okay, little crayon action there. All right, on to our last problem. The last problem is this parentheses to cos squared minus 1 quantity squared, and on the bottom a cos to the 4th minus sine to the 4th. Supposedly all the cosines don't seem to matter because on the right side there are no cosine squareds whatsoever. Okay, now it's very tempting to just kind of foil this and think that, hey, I'll just cancel out I'm going to have a cosine to the 4th when I square it, and I'm going to have a cosine to the 4th. I'll just cross those out. Oh man, that's tempting. Let's see what would happen if we did that nonsense. So if you kind of distribute the power, which is illegal anyway, and you go cosine to the 4th theta plus 1 or something silly. And then the bottom is cosine to the 4th theta minus sine to the 4th. Then you might cross these out, which is another illegal move. But now you're getting like 5 on top. So there are a lot of things I see students do that are not legal, nor are they helpful. Sometimes a student does something illegal and it looks very beneficial. They do what's illegal and they're like, oh my goodness, I'm done. Actually, I can't give you credit for anything illegal. So here's what you have to remember. There is no such thing as canceling. You can only factor the top, factor the bottom, and then cancel. Okay? So my first strategy actually on this problem is to, at the bottom, actually factor this. So as tempting as it is to FOIL the top, and I might still do it later, I want to actually break this down. Okay, so what is cos to the fourth minus sine to the fourth made of? Well, it's made of, if you literally factor the bottom, if you put parentheses, parentheses, it's a cos squared theta plus sine squared theta. I need a little more room here. It's cos squared theta plus sine squared theta times cos squared theta minus sine squared theta. Think about it. This really is cos to the fourth minus sine to the fourth. Beautiful. And here's a further payoff. This is uno. 1. See? Nice. Okay, that feels like progress. Okay, so now we have 2 cos squared theta minus 1, and that's being squared. This bottom is now just cos squared theta minus sine squared theta. You know, the end result here is to have no cosines at all. All right, no cosines at all. Only sines. Unfortunately, I've really got more cosines than I have sines. Like top has some cosines and bottom has some cosines. So let's think here. I have an idea. Mr. Shore is going to go down to the bottom and he's going to change this to 1 minus cos squared. Let's see what happens. You might say, why would you get rid of the only sines you've got? I mean, you're getting rid of the only sines you've got. You only want sines in the end. Why are you getting rid of those sines? Well, watch this. Mr. Shore is going to insert, instead of that sine squared, I'm going to put in a 1 minus cos squared right there. Perfectly legit trade. You can always replace a quadratic sine with a 1 minus quadratic cosine, or vice versa. All right. Ooh, that bottom, that denominator. Oh my goodness, look at that. It is exactly what we have on top. We have 2 cos squared theta minus 1 squared on top. And now on the bottom, we have 2 cos squared theta minus 1. The only difference between top and bottom is that the top is squared and the bottom isn't. So think of this as, you know, the top is like k squared and the bottom is k, right? What would it reduce to? It reduces to k to the first, right? And this is the same idea, except it's not a k. It's a 2 cos squared theta minus 1. But this still cancels one factor on top. So this all simplifies down to 2 cos squared theta minus 1. How am I doing? Oh no, I'm supposed to show that this is the same as 1 minus 2 sine squared. Oh no, I'm not done at all. That's okay. The cosine squared is 1 minus sine squared. Let's trade this again. And this gives me 2 minus 2 sine squared minus 1, which is 1 minus 2 sine squared, which is then equal to 1 minus 2 sine squared. Okay, so this is what we had to show. QED.